Australian Aviation Podcast, the official podcast of Australian Aviation, unpacking the latest insights, developments and issues impacting Australia's aviation sector.
Hello, I'm Jake Nelson. Welcome to the Australian Aviation Podcast. Now, it's been 15 years since QF32, the Qantas A380 flight that saw an engine dramatically explode shortly after takeoff from Singapore. After more than an hour in the air, the plane managed to return safely to the ground with no injuries and no fatalities. Captain Richard de Crespigny was on charge on board that A380 on that day, and he joins us here in the studio. Welcome, Richard.
Hi, Jack. Great to be here.
So, Richard, just to start with, can you give us some idea of how you got your start in the aviation industry?
I was interested in flying. My uncle took me for a flight in a Cessna 310 for about 2 hours, and I thought that was just wonderful. So that was, I had a very kind uncle. And then my father, I guess, engaged that possible passion by he took me on a tour of the Air Force Base at Point Cook in Victoria. And that was the Air Force Academy, and they had computer labs, hypersonic wind tunnels, all kinds of extraordinary science and technology. And that's where I wanted to go. I wanted to do something engineering-wise, but this was like engineering on steroids in 3 dimensions. So that made me convince myself that I had to go to the Air Force, and that gave me the motivation to work hard at school to get the marks to get in.
And so you started in the Air Force, and how was your Air Force career?
11 years. I was a jack of all trades, master of none. I flew transport, helicopter. I was in the Sinai Desert with an operation there, and I had a posting to F-111s that had me going through the fighter base at Williamtown for about 2 years. So I really saw just about every part of aviation. I loved it. And but as I said, jack of all trades, master of none. But it gave me a good grounding for basically anything that could get off the ground.
What were some of the lessons that you learned in the Air Force that you were able to carry over into your commercial aviation career?
Certainly a lifetime of learning, that you'll never know it all. The minute you think you know everything is a second before you make a really silly mistake. So you've got to be confident, you've got to be courageous, you've got to be confident enough if you're in a fighter to go a single pilot in a fighter into enemy territory and think you're going to come back. That takes an extraordinary ego. But to build that confidence, you have to be confident in the machine. That means in the Air Force, if you don't operate the machine to its limits, your enemy will, and they'll kill you. So you have to operate right to the limit of the airframe, and sometimes you lose control, which is just accepted as part of the operation. So then you have to learn how to recover aircraft that are stalled, inverted, spinning, on fire, and you have to do it almost habitually. In other words, you train in the things that scare you until they don't scare you. And I think that part of the Air Force in using the machine to its max, to understand it down to its nuts and bolts and half ball valves, and to operate to its limits, that's what I loved in the Air Force.
And so from the Air Force, how did you transition into commercial aviation?
I did a job as aide to the Governor-General in Canberra, and what I saw of the ministers in charge of defence at that time, and even the service chiefs, didn't impress me. And I thought, if I stay in the military and get to the top, I've got to be a sycophant to some of these politicians that I didn't respect. So I knew I had to get out. There was no point staying in the military. I wouldn't be able to keep true to my values. So I went to Qantas, and fortunately, it was timed. I mean, aviation goes in 15-year cycles, highs and lows. At the moment, we're in the biggest recruiting phase probably ever in aviation. I mean, it's been doubling every 15 years since the 1970s. And so it's absorbing all the pilots we can give it. And fortunately, I joined Qantas at a good time, and I had a most wonderful time in Qantas, flying, again, what I wanted in the Air Force, the biggest, the fastest, the best. So the jumbos, A330, A380. I had an absolutely blessed time in Qantas.
And about when was this that you joined Qantas?
1986.
What sort of aircraft, you mentioned the jumbos, but what sort of aircraft were you flying at the time when you started out there?
The jumbo, the 200 and 300 series, the 767 had just come into service, but I didn't want to fly a small a small twin. So I kept away from it. Interestingly, a lot of pilots fear new technology. So when the 400 series jumbo came out in 89, almost no pilots, I think I was only one or two pilots that requested to go for it. People didn't want to take a risk with the new technology. And that would be repeated later with Airbus type stuff. But so I found myself 2 times in my career jumping hundreds of numbers in seniority because I was applying for the types of aircraft that the other pilots were avoiding.
What was so new about the 400 that had all those pilots so skittish?
Right. The 100, 200, 300 series jumbos had a flight engineer's panel. You had 1,000 systems, independent autonomous systems, loosely coupled together by switches. Just wires, very little electronics between it. When you went to the 400, you have a central maintenance computer that can monitor the components. In the 400, to get the reliability without the engineer, you see, you could take off with 2 parts in an early jumbo, and if one part breaks, the engineer will fix it. Now you lose the engineer. So now the 400 has 3 bits of everything. So we can lose one part even before departure, and we can still go. So that's the redundancy. We get an extra component on board. We don't need the engineer. In fact, the modern aircraft now don't even have circuit breakers in the cockpit. The space shuttle doesn't have a circuit breaker. They have these like a Control-Alt-Delete switches, and all the main power circuit breakers are down below. So the whole concept of the new aircraft is that you don't actually fix things. If it's broken, leave it turned off and continue with what's operating. So this was the change from discrete systems to, in the 400, a coordinated system of computers that now talk using buses like CAN bus or Modbus. They talk to each other and they now become linked. And in the 400 jumbo, you had a switch which was off, auto, on. And most of the switches are auto, which leaves the computers to coordinate everything. But you could always turn any system either manually on or manually off. That was a limit of the Boeing automation up until fly-by-wire.
And so as your career progressed, you eventually came to be flying the A380s. Were you among the first pilots to be doing that?
I was. I went to the A330 about 6 months after they landed in Australia. And the fly-by-wire is a new technology. And to a great degree, the world was skeptical of fly-by-wire. There have been a few incidents that I had all researched, that I researched all the incidents. And I came to the conclusion that these aircraft crashes like Habersham or Bangalore with the Airbuses, they were all caused by pilots who really didn't understand the system and were either doing silly things like Habersham turning off protections or not understanding the modes, not understanding the software. It's like starting up a flight simulator but not bother to configuring it or something. You know, you have to understand the software if you're going to use it. And the Airbus is a computer-controlled aircraft. If you turn all the automatics off, you get back to a direct law, which is like flying any other aircraft, even a Cessna. But if you're going to have the automatics on, you have to understand it. And that takes a skill. You see, a lot of older pilots, and we're going from jumbo perhaps to these 330s and 380s, the older pilots, if they're not used to studying, lose the ability to study. And so they find changing modes and changing the philosophy that you do between Boeing and Airbus very challenging. So it's totally different operation. And the best way to summarize it is the word embrace. That when you convert to Airbus, instead of saying, hey, look, this is crazy, Boeing do it this way, Airbus will say, embrace it. It's a new philosophy. You just have to let go of the past and come into the new. And that was a phenomenal change, a very exciting change. And I've had a computer company for 40 years, so I'm used to software and databases and all these systems I have in the aircraft. So to me, it made sense. To me, it was really logical. And so I'd love the transition from a almost manual Boeing 747-400 to the new generation of computerized electric networked Airbuses.
And we've got an Airbus A380 here from Qantas. This is a model of VHOQL, I believe. how did you find those A380s to fly? You mentioned sort of the difference between the sort of largely manual 747s. What was it like in those early days of the A380?
Oh, look, it's absolutely. It's good you got a model here because we could just go through it. It's the most extraordinary machine. I was very good friends, or still am, with the person who designed all the aerodynamics. So it doesn't have supersonic. The jumbo has supersonic flow over the front, and that's why it's noisy in the cockpit. The airflow is controlled all the way. You've got quiet engines. You've got soundproofing. You have multiple air ducts. The sound in a tube with air is proportional to the velocity of the power of 8. So in the jumbos and the 777s, a few ducts, very fast air, very noisy. And in the 380, there's lots of little ducts going slowly. And that's why it's 72 decibels on an A380. It's 72 decibels on the A320 LR that Qantas has just got. So it's just as quiet. All the other aircraft are noisier than these two aircraft. So the A380 is quiet. It's got 3 ailerons at the back of the wing, and they move independently because if you want, you can imagine the wing being an elastic band, and you have to fly every part of that wing through the air, and the wings are going up and down, they're nodding, and they're gyrating in multiple directions, which might be part of the clue to the latest incident with the freight aircraft. So you have to manage the all the vibrations, all the torquing and twisting of the fuselage. And so these ailerons dance. It's called the dance of the ailerons. They all move independently, and it looks like magic. What you can't see is there's a dance of the rudders, that when you put an aileron control in, the rudders will move in mysterious ways. So even that part is magical to watch. It turns out the wing's probably 10% too big and the tail's a bit too big because they designed it for a stretched aircraft, but that did not occur. And that's part of the cost. The reason why the 380 is not so efficient is because it's overwinged, and also because the engines now are 10% less reliable, less efficient than the new engines. There is nothing wrong with the 380, and if you take it hub to hub, it's the only aircraft that will transfer passengers when you're in a slot-limited airport or saturated airspace. But because of the engines and the wings, it's about 10% less efficient than the new jets, and fuel makes up 30% of the cost of an airline, and that's why some people question the A380. But apart from that 10%, the A380 is the most extraordinary aircraft ever built.
And I think Sir Tim Clark from Emirates has been agitating or making some noise about there should be an A380 Neo. Do you think that's likely to happen?
Yes, look, I think the Americans had a view with Concorde. It's not invented here, so we don't want it. I think the Americans also had the same view with Airbus, although they're now embracing the A220 very well in America. And the Americans
I mean, that was invented in Canada, I think.
That's right. But the Americans tend to do point to point, and Airbus has realised the A380 is 10 years too early because Airbus forecast that the airports and the airspace will be saturated, all right? It's saturated now in America. That crash in Washington with the military helicopter, there were lots of warnings, there were lots of near misses, they ignored it. The airspace is congested, all right? Now consider that both Boeing and Airbus just put out their 20-year forecasts, and both of them agreed, or they independently said there's going to be 2 times the number of aircraft in the airspace in 20 years' time. How are we going to achieve that? That's a hell of a challenge. I doubt the Americans can, but in Europe, what we'll do is there's more requirement for these big aircraft to take lots of passengers. Look, the Neo would have been a great idea. There weren't enough takers for it. Look, the average flight time of the 380 is 8 hours. It's only 8 hours average flight time, and that's probably a big influence by Emirates. My point is this aircraft has too bigger wings with too bigger fuel tanks, too much drag for the way it's flown. If they had smaller wings, smaller fuel tanks, less drag, the A380 would absolutely blitz the market. And bearing in mind too that this is the last of the 4-engine aircraft because they're difficult to design and also they're expensive to operate. So we're now in the realm of 2-engine aircraft. So the 350 and the 777X, they're the aircraft that will take take us into the next generations of aviation. And they're actually better fitted for the atmosphere. The 380 is just a little bit too heavy because for the speed, if you had to fly it at its optimum speed, it'd be up in the Mach 0.9 area, so there's too much drag. So the 380 is too heavy, but the 777X and the A350 pretty well have an ideal weight for this atmosphere that we have with the gases and the speed of sound. And so they will be the most successful aircraft we're going to see for a long time.
But the A380 has served Qantas pretty well over the time that it's been around, hasn't it?
Look, people love to criticise the A380. I've always loved it. In fact, I've never talked about it being the wing being inefficient. When the 380 was coming, I was writing a technical book about big jets. So I went to Airbus and said, this thing's overwinged. It's not going to be efficient. And I ended up talking to the Frank Ogilvie, the aerodynamicist who built the aircraft. And we agreed it's overwinged, but we looked at all the compromises. So people will criticise the A380 perhaps because if it's not full, it's an anchor, which is terrible. But if it's full, there's nothing that will touch it. The 380, I believe, the most successful sector where it makes the most money is from Dallas to Sydney, and they're blocking off 100 seats to do that. In other words, they're not using all the seats, but it's so even with the number of seats they have, which is probably 384 seats, are still making a lot of money. It's the first-class passengers that pay for all that fuel on the flight, and they'll load about 250 tonnes or 350,000 litres for that flight. A lot of fuel, but it's air travel's efficient. It's still much better than driving or getting on a ship, and so these aircraft will remain and efficient. And for Emirates, that is in the middle of those hub operations, the 380 is critical to Emirates' success.
Well, on that note, we're going to go for our first quick break. But when we come back, we're going to be talking more with Captain de Crespigny about QF32. We'll be back in a moment. All right, welcome back. You're listening to the Australian Aviation Podcast. We're here with Captain Richard de Crespigny, who was the pilot on board QF32 on that fateful day 15 years ago. So, Richard, talk us through how things started on that day, how everything, it seemed like a normal flight at the beginning?
It's 15 years ago today, and that amazes me because it doesn't seem like 15 years. Ever since that day, every day since then, I've been reminded of that flight. People contact me. I've got a lot of friends of passengers who were on that flight who became friends. And so my life absolutely changed. I mean, I used to have black hair, but now I get to talk about resilience and really why that flight was such a success. For the black swan incident that it was, which we lost 650 wires, half the networks, 21 out of 22 systems affected, massive flight control damage. In fact, there were so many things that were broken we didn't know because the sensors were broken to tell us. So all our landing performance was never correct. We never landed with the right performance, but we did control checks in the air. We did all these procedures to mitigate for some of that. And in hindsight, I think all of the 100 decisions we made in the air during that event were turned out to be true. It turned out we made the right decision. So it's not a compliment to me. It's a compliment to all the crews, the pilots and the flight deck, the cabin crew, 8 teams. QF32 was an absolute team success. So I've had pleasure in explaining to people what resilience is, whether it's personal, corporate or national, and why QF32 was resilient. We're going into all those different aspects. It's complex. We get into human factors, which aviation has almost the patent on. Human factors is how people are built, what we can do, how we react to external things, and how you build machinery to interact with it. So aviation has studied human factors so that the humans and the machines operate safely, and aviation's clearly the safest transport mode in the world. We only lose 500 people a year out of 4.5 billion that fly. So yes, of course, it's not good to lose them, but in terms of safety compared to anything else, certainly any other transport, it's remarkably safe. So my life after QF32 has been to talk about these elements of resilience and try to help people and particularly in health, the health industry that struggles with human factors, to try and help them build up their resilience as well.
You mentioned a black swan event. What is a black swan event in aviation?
A black swan, curiously named after the black swans in Perth. The colonisers came to Perth thinking that all swans were white. So they were shocked. They didn't know it existed. So a black swan event is similar to that. It's an event that you never thought would happen, unthinkable. You just couldn't imagine it. Very low probability of happening, but it has a significant effect. So the 9/11 for most people was a black swan event. The global financial crisis for most people was a black swan. QF32 was a black swan because when that engine number 2 exploded, certification says the aircraft designers have to be able to take one piece of that disc that explodes. Generally, it explodes into 3 pieces. You have to only take one piece and survive. So the aircraft manufacturers like Boeing and Airbus say that has infinite energy, that piece, and we have to stagger the engines forward and backwards so that that exploding engine doesn't take out the others. And we have to have defenses in the fuel systems. Any critical system, we have to survive one piece, right? So the A380 was designed to take one piece and survive. But we had 3 pieces that hit the aircraft, and it took out all those wires, half the networks, and so the damage was much in excess of what any certification standard has. Airbus aircraft certification takes you up to 1 in 10 to the 9, 1 in a billion flying hours. We were 1 million times less probable than that, and so it was unlucky. It was a black swan event, but I just have to reinforce that the design of this aircraft was extraordinary, and I had pleasure in giving an address to 600 people, leaders of Boeing, and I had pleasure in saying that I gave a presentation to the 600 leaders at Airbus at their annual conference, and I stood up in front of them and I said that 469 passengers and crew, and for every person that died, there'll be 70 people that will go to their funeral. So I multiply 469 times 69, and I said, so 32,000 people would like to thank Airbus for building a resilient aircraft. And that's what I honestly think. I think all these Airbus fly-by-wire aircraft are amazing. They're efficient, and I have the highest respect for them. And in the case of QF32, it absolutely proved itself resilient.
So we're talking about, you mentioned the human factors, you mentioned how humans react. That moment in the cockpit when you heard the bang as the engine went up, what was the reaction in the cockpit? How did you guys respond to that as suddenly everything went straight to hell?
Jake, if there was a thunderstorm outside and you hear a thunderclap, you would say, that's thunder. Okay, I've heard it before. So if you practice the things that scare you in, say, simulators, they don't scare you anymore. If you practice things enough times, they become habits. So pilots get into simulators, we practice the things that scare us, like engine failures with explosions. So when that explosion happens, the amygdala, or the emotional part of our brain that pattern matches inputs quickly, within 20 milliseconds, says, that's an engine failure, and I know what to do. It's not the end of the world. The cortex comes online a second later saying, I know what to do. This is what we have to do. It'll inhibit the fear response of fight, flight, freeze. The cortex comes in saying, this is what we do for the engine failure. Bang, 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 bang. A series of habits. So that's why it's critical that we put pilots in simulators. It's critical we practice the difficult things until they become not just habits, but they don't even stress us. And sometimes you really want pilots that have been pushed to the edge, to have experienced fear and pain and suffering, because that'll be burnt into their psyche. It'll adjust their risk appetite, and they'll be more cautious going forward. So training of pilots takes over a decade, and hopefully you come out with someone that understands all the elements of resilience and particularly risk, and they will have a chronic unease for the status quo, expecting things to go wrong, but confident that they can fix it.
And what happened? What did you all do in that first 30 seconds?
Okay, what we didn't do is go into a checklist. That's absolutely irrelevant. What you must do, and because it's the amygdala that's creating the fear response, right? If you don't keep the aircraft flying, then you'll crash. So before the cortex comes online in about 30 seconds, you have to stop this fear response. So the pilots are taught aviate, navigate, communicate. Aviate, fly the airplane, just keep it alive. So I press the altitude hold button that would cause the aircraft to level and the thrust should come off. I press the heading hold button that stops it following a curved departure. And then I watch the speed. The speed's increasing. I don't know why. We're about to overspeed. I grab the thrust levers and I pull them off. Now, bearing in mind, during this whole process, the alarm bells are going off. 40 checklists are being queued up in the ECAM system, which is a checklist system on the Airbus. And alarms are going off. We can't cancel it. There's lots of distractions. We have to focus on aviate, which is what I've just said, navigate, find a safe place above the mountains, get to a safe part of the airspace, then communicate, then talk to people. So for the first 30 seconds, nothing was said until I'd finished that first cycle of aviate and navigate. And then I said, the altitude's constant, we're above the mountains, the speed's constant, and the heading's constant, we are safe. ECAM actions. And ECAM actions tells Matt, the first officer, okay, now you can go by yourself, head down and start actioning the checklist, and I'll keep flying the aircraft and monitoring you. So that first 30 seconds is critical. We don't look at controlling an engine fire. That can wait. We just have to make sure we're alive. In a crisis for a business, a lot of them often get so focused on the crisis, they either run out of cash and go insolvent, or in the case of some of the famous aircraft crashes, they get tunnel visioned on a broken light globe that they can't resolve and they run out of fuel and they crash. So this is what aviation has learned through all the human factors of all the crashes that have killed people. Regulations and laws are written in blood, and this is what we do now to cover it. And again, the crew, not just me, the whole crew, I'm proud of what they did. We worked as a unified team, and I think we did a great job.
So that first 30 seconds is over. You have aviated, you have navigated, you have communicated. You are safe. The aircraft is stable. What came next?
Running through the ECAM, Electronic Centralized Aircraft Monitoring System. The aircraft has 250,000 sensors and parameters, and the ECAM is a computer program that listens for those error messages, pulls up a database of what the problem is, and hopefully tries to fix it, or stop it, fix it, or mitigate it. So ECAM is threat and error management laid out in a linear way. And so Matt's running through it would take him an hour before he gets to the end of the first pass of ECAM, and his voice fails because he's talking through it. We had many ECAMs. Now, I have to tell you that we had so many sensors broken, a lot with just getting technical, with the CAN bus, which is a bus designed by Bosch for cars, but they use it on aircraft to bring in third-party products. The CAN bus is a 2-wire network, and if you break a wire, the gauge reads 0. Now, is 0 a 0 oil pressure, or does it say there's no data? And that was the problem with CAN bus. So we had broken wires, and we saw many displays on the aircraft in the cruise where we saw the air pressure over an oil tank and the oil pressure level coming down, then low oil pressure, then the ECAM system failure, turn off these pumps. We didn't find out till 4 months after QF32, every one of those indications were incorrect. People say we should have got off the aircraft because there was 4 tons of fuel dropping down their hot brakes. They're assuming. Pilots never assume or presume. We didn't have sensors. They were crosses. You assume the brakes are hot. We waited for someone to say there was fire before we wanted to evacuate passengers down the aircraft into a really dangerous situation. We were never told there was fire. Turns out 4 months later, and I couldn't write any of this in QF32 because it was privileged information to the Transport Safety Bureau. 4 months after the event, I find out that all those brakes near that leaking fuel were cold because all the brake wires are broken. The brakes never came on. It just comes to reinforce you don't presume or assume. You're driven by facts. You fight the enemy in front, and all your decisions are based on facts, not presumptions. So Tom Enders, the CEO of Airbus, wrote to me apologising for ECAM, saying, I'm sorry you had so many incorrect checklists. And there are many more I could talk about, but there are many checklists that we actioned straight away. There are many checklists that we thought about and continued with, and there were many checklists that we absolutely ignored, because if we'd followed those ECAM checklists, we might not be here today. And so that, again, reinforces to every pilot that you must understand your system down to their foundations. You've got to understand that when the automation fails, you need a secondary or tertiary way to see what's working. And of course, always just be driven by facts.
So what had, we touched a bit on it, but, looking at the model here, what had actually happened inside that engine, and what damage did that do?
All right, this is really interesting. It just shows how tiny, a butterfly flapping its wings can cause a cyclone on the other side of the planet. So there was an oil pipe running from the outside of engine 2 into the internals to feed a bearing support for the shafts that run through the center of the engine. The oil pipe came in from the side and connects to a stub pipe, which was just a short pipe to connect into the bearing mount. That stub pipe where this thing plugs in had been badly manufactured. There was a crack. It was thin-walled. It cracked. Oil leaked into a part of the engine that should be dry, nothing in it. But it sits, the cooling air that keeps it cool is at 800 degrees Celsius, right? And that's a cooling air that feeds into the turbine blades. But 800 degrees, the oil auto ignites, catches fire, gets hot around the shaft, hot around the hub for the turbine. The hub gets weak, soft. The 50,000 horsepower that the turbine's taking out of the air twists and torques it off the shaft, comes loose, overspeeds. There's meant to be cookie cutters that as the turbine moves back, the blades get cut off. That didn't work. The fuel system actually detected a lower thrust, and so put more fuel into the engine. So the first, there are a series of bangs, but the second bang was this turbine overspeeding. It's meant to run at about 7,500 RPM. Who knows what it was at? It increased in radius by 1 inch. Pieces came off at 2.5 times the speed of sound. 3 pieces hit the aircraft. I mean, the whole disc is 160 kilograms and a metre in diameter. So this disc came out, energized all these other particles, a bit like energizing a cluster bomb. Now, there are 2 torque tubes that hold the engine onto the wing to stop the 72,000 pounds of thrust from ripping the engine off the wing. They were both broken. We're lucky the engine didn't rip itself off the wing and do what happened to the latest aircraft, freighter aircraft. There were 400 impacts on the aircraft, 100 under the wing, 100 on the leading edge, 200 above the wing. There are impacts up to the top of the 8-metre high tailplane, 400 impacts. For passengers, it sounded like someone's throwing a bag of marbles over a corrugated roof. Those pieces came through the wing, through 15 millimetres of aluminium, through a fuel tank full of fuel, creating shock waves, fracturing the earthing leads, creating chaos in the fuel tanks. We had multiple holes in multiple fuel tanks, multiple leaks in multiple systems outside limits. And there were, again, the networks, but the resilience of the aircraft, all the wires that were broken in the leading edge, there were backup wires that went down through the belly to the trailing edge. Unfortunately, the third piece that came out of the engine went through the belly and took out 2 wiring looms of 250 wires each, took out a lot of the backup looms. That's why we started to lose spoilers. We lost 65% of our ailerons. We lost our leading edge slats. We lost most of our brakes. I could keep going for a long time. I'm trying to keep it short.
Yeah, it's... In those circumstances, how do you get this giant plane with 400 passengers on board back on the ground?
I actually lost my my mental model. You have a mental model of having arms and legs. You can close your eyes and touch your nose with your finger because you have a mental model. And when you drive your car, you know where your wheel is to within 2 inches of hitting the curb. Well, pilots have that too. When you know the airplane, you wear it like a glove. Feels like part of your body. And when things degrade, there are 4 million pieces on an A380. And as the checklist came out and we're losing systems, I'm adjusting my mental model. And eventually there were so many primary failures and secondary failures. I mean, the secondary failure is we've lost 65% of our roll control. Now that's all right, but now we've got 3 fuel imbalances that are out of limits. ECAM didn't say, hey, are you going to be able to control this aircraft when you come in to land? We've lost the leading edge slats, so we have to speed up. And it says, that's okay if I've got brakes, but the aircraft didn't know we've lost 60% of our brakes. Question is, will we be able to stop on the runway? So my mental model was collapsing because I couldn't keep track of the primary and secondary failures. So what I did, and the other pilots said that they didn't, but that's okay, I reversed the logic, which is what happened with Gene Kranz and NASA during Apollo 13, where when you've got a complex system, let's say 4 million parts, let me take the case of Apollo. Apollo 13 going to the moon, the oxygen tank explodes. The actual spacecraft had 10 million pieces on it. And the mission controllers in Houston, average age of 26, melting down with all the error messages. They didn't know what was going on. They were so confused. And Gene Kranz stood up and he said, "Gentlemen, stop wondering about what's broken and focus on what's working. Invert the logic. Look at what you've got." They did it in Houston, and Apollo 13 is probably the most successful failure in human history. We inverted the logic on QF32, and then all we knew is forgetting what's broken. We didn't need all the transfer galleries of fuel management computers. We didn't need boost pumps. We just had fuel sitting over the engines that could drip down into those engines. And so when you invert the logic and just say, we've got 1.5 hours of fuel in that tank before that engine runs dry, or it was 2.5, and 3.5 those engines, because we had a lot of fuel leaks here, time gives you options. So you try and find fuel as pilots because fuel gives you time gives you options. So when we inverted the logic and I knew we had 2.5 hours before this guy goes quiet, the stress came down. Now it became understandable. Now, we're building like a Cessna or a Piper aircraft out of a junkyard, but you don't need much. And providing you understand aircraft and you're confident hand flying it, and you don't overcomplicate it, and you're not intimidated by electronics that might even be not working. If you invert the logic, it changed my whole mindset.
Talk us through then the landing itself. After sorting everything out, after making sure that you were safe up there, how did you manage to come back in and get that plane safely on the runway? Well,
I just have to start a few minutes before we started the approach. There was a famous El Al flight. It was a freighter in Amsterdam, flight 1980, I think. And they lost 2 engines off one side of their jumbo. They could fly around in the Holden pattern quite happily. When they came into land, when they came back into land, they put the flaps out. There was no slats here. The flaps didn't work. They'd been damaged. And so those flaps came out. The aircraft rolled inverted into an apartment block and everyone's killed. So we learned from that. I'm not criticizing these pilots. We learn from people's experiences. So I knew we had to do a control check because we had multiple holes in the wing. So the coefficient of lift, the basic measurement of what a wing can do, was damaged massively. And flight controls are taking up opposing positions to counter that roll that comes in because of it. So there was a lot of damage. We had to prove the aircraft safe to land. So we did a dress rehearsal at 4,000 feet. In other words, slowing down, putting flaps out one stage at a time, slowing down the next stage, and then slowing down, and finally the gears down. And if the aircraft starts to roll uncontrollably, I would aggressively maneuver the aircraft to see what it would do, and it was controllable. But if it did start to roll and what we call depart, then you would know that was an unwise choice and you should go back. I'm trying to prevent myself getting to this LL flight, right? We proved the aircraft safe to land at the approach speed in the landing configuration we had selected. That was the most important thing on the flight, because as we came down finals, we were getting speed warnings, which is low energy warnings, when we slowed down 1 knot. And when we slowed down about 3 knots, we got a stall warning. Now, I just have to reiterate this. You should never get speed or stall warnings in nominal operations. There should have been a 23% margin, maybe 19 with no slats, 19% margin between our approach speed and the stall speed. We should never have heard that. So we're coming down hearing the speed and stall warnings, and alarm bells are going off saying, what in the hell is going on? You have to understand this. The stall warning is directly off angle of attack sensors, no computers that can affect it. It's a real stall warning. Something was really wrong. If we had gone around because we weren't happy, obviously something wrong with all our approach stuff. We're coming in far too slow. If I'd gone around, engines 1 and 4 that had no overthrust protection would have destroyed themselves, and then it'd be all over. But we made that We did the control check. We proved the aircraft safe to land. We continued through the speed and stall warnings. I just pushed up one of the thrust levers a little bit. I mean, this is a binary logical aircraft, so 1 + 1 knot can stop the alarm every time. I just knew I had to be careful. The point I'm saying is those control checks to prove the aircraft with an unknown wing. What the aircraft we landed with was not an A380 wing. It was some other wing was a wing that had been damaged and produced less lift. But we proved it safe and we landed despite all the warnings that we got.
And you had, obviously there's only so much runway that you have available. What were the calculations like on how much runway that you had to get that airplane to stop safely?
Right, so Dave Evans, the check captain, he was in charge of all the calculation landing data. He initially said we can't do it. It won't calculate it. It just refuses. So we took out a lot of things that we thought weren't relevant, and eventually Dave came up with 130 metres. That means at a 4-kilometre runway, we would need 3,870 metres. And people say, that's terrible. And I say, no, invert the logic. We have 130 metres. We just have to understand how the test pilots certify the aircraft, and which is 7 seconds and 50 feet to touchdown. I mean, pilots should know this stuff, right? In case this comes up, 7 seconds from 50 feet to touchdown. If you can do that, you're following the certification. That's what I knew. In fact, we did 5 seconds from 50 feet to touchdown. So we touched down early. But I knew that this is how we'd have to land it. And when we did put on the brakes, because there were so few brakes left, and only half the spoilers, and the ailerons wouldn't act as speed brakes, then I knew that, well, it was very slow deceleration. But eventually it did stop, and we stopped about 100 metres from the end of the runway, and then 8 fire trucks immediately surrounded us to protect the passengers if we had to evacuate.
All right, well, we're going to take one more quick break, but when we come back, we're going to talk a little bit more about what it was like once that plane was safely on the ground. All right, welcome back. You're listening to the Australian Aviation Podcast. We're here with Captain Richard de Crespigny of QF32 fame. So, Richard, the plane is on the ground. It is safely stopped, but you in a talk earlier this year at Airport Safety Week, you mentioned that the plane being on the ground was in some ways harder and more harrowing than being in the air. Why was that?
Yeah, Dave Evans, the check captain, thought it was much more dangerous on the ground than in the air. Now, I don't agree with that, but that's fine. Everyone's perception in an incident is different, right? And they're all true. Now, Dave's perception was, well, my perception in the air was, how are we going to land this thing and what were we going to get at the end? Because when people criticize us for staying in the air for 2 hours, but you have to understand on a network electric aircraft that what you get at the end depends on logic written by maybe a university graduate straight out of uni who's never been on an aircraft. So you can't assume anything. So we spent 2 hours to work out what we were going to be left with to land. After we landed, I was just about to pat Matt on the shoulder and say, well done, it's over. But it's like a bushfire where the wind changes direction. And now we get 20 more ECAMs that start up. When we shut down the engines, the APU that's meant to give us electrics and pneumatics, neither of those work because of multiple damages. So now we've got a hot cabin and a 30-degree Singapore day. We've got no electrics. We lose 6 out of our 7 radios. We lose the radios we're trying to talk to the fire controller with. We lose 9 out of our 10 screens. And eventually when the fireman says, no, he won't approach the aircraft because we've got to shut down the engines, that's after we managed to finally contact him with the last working radio. We said, no, the engines are shut down. He said, no, they're not. And I stuck my head out, and engine number 1 is still turning. We'd lost the wires. We'd lost 2 systems, each using 2 independent pairs of wires to the low pressure and the high pressure shutoff valves in 2 different parts of that strut and engine. So, in other words, the black swan got worse because now we can't shut down that engine. Because this is the pilot's network, if we'd lost the 2 wires to control thrust, if we'd lost that in the air, then you could work through the what if, and you probably reason that I wouldn't be here to talk to you today. So we did have control of the thrust. We didn't have control to shut it down. Now we had an engine that's out of control, and if the passengers come down the slides and walk in front of the engine, they could get sucked into it. There were 4 tons of fuel over the ground. People thought there were lots of hot breaks. There were so many threats. The bottom of the top doors where you'd stand, where your feet are, is 8 meters off the ground. Go to your swimming pool, go to the 3-meter diving board, go up 2.5 times, put a slide down there at 45 degrees, and then put your grandfather on that slide, Jake, who came onto the aircraft in a wheelchair. The risks were profound. And ultimately, one of the elements of resilience is decision-making. This decision as to whether to evacuate or not, which is probably Dave's thought, this was the most difficult decision probably we've ever made in a career. We decided to keep people on board because that's where it's safe. But you have to understand, you've got to know things like the chemistry of the fuel. What's the flash point of fuel? People think jet fuel's like gasoline. Well, it's not. The flash point is plus 35, where it's minus 40 for gasoline. The burn rate is if you cover your floor in gasoline, the flame will move at 200 meters in a minute. Kerosene or jet fuel will move at about 30. So you need to understand all these different risks and threats. Bearing in mind we've got 8 fire trucks surrounding us that are not there to protect the aircraft, that if the passengers are going down the slides and they look like they might catch fire, the fire engines will stop the passengers catching fire. When you understand the way that the fire service is set up, you understand what they're going to do, you understand the certification of getting 853 passengers out of half the doors in 90 seconds, and we only had 440 passengers. When you put all this into your risk calculator, we came up saying they're safer on board, right? Now, you get this sort of intuition after being a pilot in the air for many, many decades. And we had the most extraordinary pilots in the cockpit that day. And again, that decision to stay on board was correct. We got 440 people off that aircraft with 0 injuries.
And what was the aftermath of all of that? It's one of the most incredible landings in the last 25 years. It could have been a spectacular catastrophe, but no injuries, no fatalities. How did things progress after all was said and done?
Yeah. At the end, when we got the passengers off the aircraft after 2 hours, so it was 2 hours in the air, 2 hours on the ground, they go to the terminal, and now we spend another 4 hours debriefing passengers in 3 different areas, telling them what had happened, why, what was about to happen, what they needed to do. And I told the passengers that the media outside ready to say that Qantas is a lousy airline, Rolls-Royce make lousy engines. And you see, I was writing a technical book on big jets, so I said, jet engines only fail 1 in every 300,000 flying hours. That means that only 1 in 4 pilots of a quad aircraft will ever see an engine failure in the whole career. So be grateful you've seen this, because you're protecting your friends and neighbours from seeing an engine failure, right? So I gave them reasons, and I told them the reasons why we're airborne so long, the reasons why we're on the ground. And then the last thing, this is the last thing, that good luck in a crisis finding a telephone number of the company that's involved, right? Because you won't find telephone numbers for big corporations anymore. So I said to the passengers, if you think that the Qantas is not doing what you want, if you think that Qantas doesn't care about you, these are 2 considerations in the mind of the other person, then here's my mobile number, call me. So I gave my mobile number to every passenger, and to this day, 15 years later, 0 have called to complain, 0 have called to ask for help, but about 20 people used it to say, hey, thanks, can we have a beer? And each Christmas I get letters, a friend, one of the passengers have become friends for life, and one of the passengers sends me a subscription to National Geographic. She renews it every year. So many of the passengers have become lifelong friends. Many send me pictures of their families that they would say thank you, because I have this family now because of you and your crew. And the after effects of QF32 will go on as long as all these passengers are alive. And I just have to reiterate, if I haven't made it clear enough, that there were 8 teams in this event, and I have to thank all of them, including the passengers, for basically turning a black swan event into an incident where the Qantas brand that was under threat at the time, because it couldn't get a trick with the media, the brand came out after QF32 stronger than when we went in. There's not one picture anywhere on the internet of one single passenger crying coming out of that event, out of that black swan. And that's because of these 8 teams. And that's why I'm happy here to talk to you and to sing all their praises.
So at Qantas and at Airbus, obviously I think in the immediate aftermath, the A380 fleet globally was grounded. What happened? What do you think that Qantas and Airbus took away from what happened on QF32?
Rolls-Royce initially went quiet. I think they've learned that lesson that in a crisis, you see 60% of the time people expect a crisis because 80% of the time you caused it. If you look at the Boeing MAX incident, Boeing knew about the MAX problems but was saying nothing through, even weeks after the second incident. So there's a lesson learned. You have to get on top quickly with the media. You know what's gone wrong because you probably caused it. Get out there, get the facts out there, get the reasons out there. This is why I compliment Airbus 1,000% on the reason for grounding the A320s this week, right? They took a difficult call knowing they would cause chaos, but people have a fear of flying, and Airbus have done the most remarkable thing in grounding the fleet, and I compliment them. And people should be lucky that there are manufacturers like Airbus that take responsibility fast and ground a fleet when we compare it to other manufacturers that haven't.
And in the aftermath, you as well, you've left aviation. You've written this book, Fly: The Elements of Resilience. You have. I think you work as a speaker now. Just to wrap everything up, what is the biggest lesson that you have taken away from QF32 and everything that came after?
The biggest lesson is that it's easy to be successful. You just have to be passionate, execution and discipline. But you could be the best stagecoach driver, but no one wants to drive stagecoaches anymore. So you need to be more than successful because it's a disruptive world. Everyone's being disrupted. And the aim is we assume things go wrong now. So many things go wrong. We have to be resilient. We have to recover and come out stronger. We have to learn from our mistakes. Resilience is what we must be if we want to survive in this new world. And so the elements of resilience apply to us personally, corporately, nationally. If you look at the country, we've only got, say, 15 days of jet fuel at the moment in the country, 15 days to service civil and military purposes. 90% of our oil comes from foreign countries that we have no control, on foreign ships that we have no control over. This is not a good example of resilience, right? We have between 20 and 30 days of gasoline and diesel. And when one of the only last 2 refineries shut down briefly a few years ago, after day 2, the people in Gippsland were driving up to New South Wales to get diesel. My point is that we must embrace all these elements of resilience, understand them, and if we want to be successful, if we want to survive, understanding that we're going to fail many times because we have to make decisions in this time of disruption. Resilience is everything, and we have to embrace it. But if you do, you won't just survive in the bad times, but in the good times, you'll absolutely thrive.
Well, on that happy note, Captain Richard de Crespigny, thank you for coming on the Australian Aviation Podcast. Incredible story.
Thanks, Jake. It's a pleasure to talk to you.
That is about all the time we have for the Australian Aviation Podcast today. I'm Jake Nelson, and we will see you next time.